We have the second lecture by Valérie. Does anyone have a problem with the whiteboard? You know, the reflection? I mean, because yesterday was in some angle that some people had some problems to see it. Nobody? Okay, if not, let's let Valérie start. Thanks.
Again, too early in the morning, but let's see what we can do. So let me briefly recap what we did yesterday. So yesterday we were talking about stuff that we actually know. Today we'll very quickly get into stuff that we don't know and where we can just kind of develop models and think what could have happened at those early times. But yesterday we worked our way backwards, starting from relatively late time, so low temperatures. We talked about the CMB. We talked about how from the homogeneous part of the CMB we can measure the temperature today, and then together with the physics of the CMB we can calculate the time of matter radiation equality. And then going back even further, we talked about BBN as a very sensitive probe to particle physics at the MeV scale. So today we're going back even further in time, and we'll talk about baryogenesis. And already yesterday, when we talked about CMB and BBN, this number of the baryon to photon ratio came up a couple of times. So we saw that we can determine that both from the CMB and from the BBN measurements. And it tells us the amount of, or the number of baryons today compared to the number of photons today, and it is this number of 10 to minus 10. And now this number is kind of what we would like to explain in today's lecture. And so the first way you could think of explaining this is to say, okay, so the puzzle behind this is that if you think you had some hot thermal plasma in the universe, you have particles and antiparticles which have the same mass and hence are produced at the same abundance in thermal equilibrium, and then as the universe cools down, these particles will annihilate into photons, and at some point you would basically naively expect a very empty universe with no particles and antiparticles left. Now that's not exactly true. There will actually be some particles and antiparticles left, and that is simply due to the freeze-out process, because at some point a particle will not find its antiparticle simply because in the expanding universe it's too far away. And from that alone, one can compute how much matter we would expect to be left over from the freeze-out process of matter itself. So you heard a lot about freeze-out computations, both from Tracy and from me, and we'll do it again, because a lot of cosmology is basically doing the same calculation over and over again. But this time we will talk about nucleon freeze-out. So again, there will be a subscript n, which is not neutrino, it's not neutron, it's nucleon this time. And very similar to what we did yesterday, as long as the nucleons are in equilibrium with the thermal bath, so nucleons in equilibrium, then the number density of neutrons is the same as the number density of antineutrons and is given by the usual Maxwell-Boltzmann distribution. So we have a factor 2 for the degrees of freedom, nucleon mass, temperature over 2 pi to 3 over 2, and then e to the minus nuclear mass over temperature. Now, freeze out occurs when the rate that is keeping these guys in equilibrium is equal to the Hubble rate. So when Hubble is gamma, where gamma is the rate at which the nucleons go into photons and back again. So this is just the annihilation rate, where you also saw the formula yesterday. So the number density of nucleons, the annihilation cross-section velocity averaged. And okay, this is mediated by, so this is roughly going to be the pion mass, determined by the pion mass. And then this is the computation of, this is basically the dark matter freeze-out computation, right? Just now that we're not doing it for dark matter, we're doing it for nucleons. So Tracy went through this in a lot of detail yesterday, and she explained to you that okay, you know how the Hubble parameter scales with temperature in a radiation-dominated universe. Whoops. You plug that in here, and then you can determine the freeze-out temperature in terms of the other mass parameters of your model, right? That's exactly the same as what happened for the WIMP freeze-out computation yesterday. Now, of course, we don't put the 100 GeV or so or TeV for the dark matter candidate. Instead, we put the mass for the nucleon. So neutrons and protons, right? Well, protons mainly. And then we get the freeze-out temperature of 20 MeV out of this. Very same computation as yesterday. Okay, what does that mean? That means now we can take this freeze-out temperature, plug it back in here, and we will have the number density of nucleons after freeze-out, which will then stay constant up to redshifting. So the co-moving number density will stay constant after this temperature. So then we can compute the number density of neutrons divided by the number density of photons. Right here, the number density of photons is just the thermal abundance, right? So something like 2 zeta of 3 pi squared temperature cubed. Okay, this will of course be the same as the number density of antinucleons, right? Because the only thing that ever entered was the mass. It's going to be the same. And then we just take this expression, plug in this temperature. So 2 pi squared zeta to the 3 nucleon mass 2 pi freeze-out temperature. So it went downstairs because we divided by temperature cubed here. E to the minus nucleon mass over the freeze-out temperature. These are now all numbers that we know, right? Because we know the nucleon mass, we know the freeze-out temperature. We can compute this, and we find a number of 10 to the minus 18. So, what does this tell us? This tells us that there are indeed just remnant protons or remnant matter left in the universe, simply just from freeze-out, without putting in anything else. However, this number is significantly smaller than the 10 to the minus 10 that we've seen from the measurements of BBN and CMB, right? This means that we cannot explain the remaining matter in the universe simply by a freeze-out process. What we need is that because we didn't do much here, right? We started from this equilibrium distribution, we just computed the freeze-out. So what we need to do in order to get the right number here is we need to basically violate this condition at the very beginning. We need to put here some tiny difference between nucleons and antinucleons, and we can also already kind of see roughly what order of magnitude that this difference needs to be, right? It needs to be able to explain this discrepancy here. So we need to put a tiny asymmetry between nucleons and antinucleons of the order of 10 to minus 10. And then when everything kind of tries to annihilate, that will be the asymmetry that we're left over at the end. So conclusion here is that we cannot get this number simply from freeze-out, but we need the number density. And I'm writing nucleons here, but you could also write baryons directly, because that's the stable particles in the standard model. So we need to get this value not from freeze-out, but we need to get this value actually as an initial condition. And I put initially in quotation marks, because it just means that at the time of nucleon freeze-out, right, this asymmetry needs to be already there. But when exactly it is generated, right, will depend, as we will see, will depend on the concrete model in question. Any questions on that?
When you compute the freeze-out temperature, 20 MeV, you're assuming that the Hubble rate equals the exchange rate or the interaction rate by, and it's roughly the mass of the pion inverse squared.
Yeah.
Why? Why is it the mass of the pion inverse square?
Well, it's because it's the nucleon annihilation rate, right? So it's a bit the dimensional analysis, right?
Okay. Okay.
I didn't derive it, right? You could actually derive the annihilation cross section. I didn't do that.
Okay, but it depends on the mass of the pion. Why of the pion? I mean, is it could it be of the particle like?
Well, just because that's the lightest exchange particle in the nucleon interactions.
Okay. Thank you.
Okay.
Okay, so that means we kind of need to get this asymmetry somehow initially, but that's also a bit strange, right? Because if we think, okay, we have some hot thermal plasma, you would really think there should be particles and antiparticles at the same abundance, right? So somehow we need to get this asymmetry into our initial plasma. And in order to do that, Sakharov wrote down on very general terms 3 necessary conditions that you need in order to get in order to generate such an asymmetry. So these conditions basically are what you need in order to generate any amount of asymmetry. Fulfilling them doesn't mean you get the number right, but that's basically what you need to do in order to get any asymmetry. So what I'm going to do now is I'm going to explain you one by one why these are necessary conditions to generate an asymmetry. And then we'll go and we'll look at some popular models. And we'll see how concretely that is realized in different particle physics models. And I hope you appreciate that I wrote very big, which means I have to wipe the board all the time. Okay, so the first one is baryon number violation. That one is a bit obvious because, okay, so what we fundamentally want to generate, because what we actually measure in the CMB is an asymmetry between baryons and antibaryons. So obviously, if we start with initial conditions, which have the same amount of baryons and antibaryons, and we have no baryon number violating process in our physics, then we will never get an asymmetry. So the first condition is relatively obvious. Now, the second condition is saying that it's not enough to have baryon number violation. You need to additionally have C and CP violation. That's a little bit less obvious. So let's have a look at what's going on. So C and CP violation. So let's imagine we have some process, right? Some initial state going into some final state, violating baryon number. Okay, because we have the first condition fulfilled. Now, what would happen if we did have C symmetry, so charge symmetry? Then we could equally write down the process that the anti-state of the initial state goes into the anti-state of the final state, and because of this C symmetry, this will happen at the exact same rate as this process. This is what the symmetry is telling us. And the amount of baryon number that we will get will be exactly minus delta B. So if we have the C symmetry, right, then automatically we would get, well, that there's no baryon number violation here. Okay, but that's not enough. We also need CP. And the reason is that, imagine if we did have CP symmetry, or equivalently, we had T symmetry. So here I'm using the CPT theorem, right? So I'm assuming that CPT as a whole is conserved, so that CP violation equals T violation, time reversal violation. But if I had time reversal symmetry, then I can again go back to this process and say, okay, if I can have this process, then I can also have the inverse process, right? So I can have F going into I, again, as the same rate as the initial process due to the symmetry. And this means, of course, also in this process, I will have exactly baryon number violation minus delta B. So again, I will arrive at the conclusion that I cannot generate any baryon number. I mean, I can generate baryon number maybe in one single processes, but I cannot kind of statistically in my entire universe generate any baryon number because I will always have the process and the inverse process occurring at the same rate. Okay, so this is the reason why we need both C and CP violation as a necessary condition to generate any bound symmetry. Yeah. Then you're putting in an initial bound symmetry, right? Because if your initial state, this is a bound number violating process, right? So meaning that the total bound number charge in this is different than the total bound number violating charge in that, right? So if you tell me I start with initial conditions where I have much more I than F, then you're telling me you're already starting with initial conditions where bound number is already violated. Then I agree, you don't need to do baryogenesis anymore. But a very good question. Any other questions? Okay, so then the third condition that we need is the departure from thermal equilibrium. So why do we need that? So let's imagine again, following the same logic, let's imagine a situation where we do not have departure from thermal equilibrium, right? Then we would just say, okay, the equilibrium abundance of some particle species X is given by, I mean, this is always the expression for the equilibrium abundance, right? But being in thermal equilibrium means the actual abundance follows the equilibrium abundance. Okay, so again, the degrees of freedom. I'm writing down now the Maxwell-Boltzmann distribution, so I'm assuming this is a massive particle, but the same, you could also write down Fermi-Dirac or Bose-Einstein, whatever you want, right? I mean, the logic would always be the same. And here we have the mass plus the chemical potential now, divided by temperature. You'll see in this, as why am I adding the chemical potential? I'm adding the chemical potential because that's the way to distinguish between particles and antiparticles. Of course, if I set the chemical potential to 0 from the start, then I'm just going to write down the same number density for particles and antiparticles, right? And then it's clear that I'm not going to generate an asymmetry. So that's the equilibrium abundance for the particles. And then for the antiparticles, all of this is the same, right? The mass, of course, is the same. But here I get the chemical potential of the antiparticle. And now to have an asymmetry, what you would need is that the chemical potential of the particle and the chemical potential of the antiparticle are different. However, now recall that we already required in this first condition that we need baryon number violation. That means that just because we had this first point, the process like XX going over to X bar have to be possible. And if we're saying we're in thermal equilibrium, it means that this process is happening kind of in the same velocity in both directions. Now, the point number one doesn't actually have to say that you have to have exactly this process at tree level, right? It may be more complicated. You may have to go through some intermediate heavy particle or through some loop or something, right? But being in equilibrium means that this process happens in both directions at the same speed. But if you have this, right, then this directly tells you, if you just write down the balance equations, this basically tells you immediately that the sum of the chemical potentials on the left has to be the sum of the chemical potentials on the right. And now, of course, you see, okay, the two chemical potentials have to be equal, which means the number densities have to be equal, which means, again, it's not possible to generate a symmetry, right? So here, from this, you see that nx is nx bar, and hence, again, you would get no asymmetry. So this is why you need all these three conditions as necessary conditions to generate the asymmetry. With the small caveat, right, that we did at some point here, we assumed CPT symmetry, right? That's the additional assumption which is in the Sakharov conditions, which is usually not spelled out explicitly. Any questions on that?
Before going to baryogenesis, is there, I mean, is completely excluded the possibility that different domains of the universe are, you know, with matter and others with antimatter? Is completely excluded
right.
At this point?
Yeah, very good question, right? So, okay, so if if we say that the universe kind of, right, is homogeneous, right, then we get back to this number of 10 to minus 18 that I had beforehand, right? Now we could assume the universe is inhomogeneous, right, and we have different patches which do that. And now you can kind of go through the different scales that we have in our universe and ask, could the universe be antimatter dominated at those scales, right? Then you start with the solar system and you say, okay, well, we've sent a spacecraft to various parts of the solar system. The spacecrafts have crashed, but they have never annihilated, right? So probably all the planets are made out of matter. And then you go kind of further and you say, okay, look, we have cosmic rays, we have observation of stars, and hence we can kind of conclude that all of that is probably matter. So then the only place where the antimatter could be would be like really far away, right? At least in other galaxies. But then you would expect that at the boundary regions of the antimatter-dominated regimes and the matter-dominated regimes, there should be a lot of annihilation going on, and you would see that as electromagnetic radiation. And we don't see that. So it's still possible that outside of our Hubble horizon, right, things are antimatter-dominated, right? That's in principle possible, right? But if we're outside of our Hubble horizon, then we're outside of our observable universe, and then we're anyway outside of where we can actually do meaningful physics, right? So then you can say, okay, you could also say, okay, there's a multiverse, and some of the multiverses are matter-dominated, and some of the multiverses are antimatter-dominated. You can say that, right? But then you still need to kind of explain this number in our universe. And as we'll see in Thursday's lecture, right, kind of inflation gives us as initial conditions for our observable universe that there should be no asymmetry in our observable universe. So we still need to generate this from somewhere. Yeah.
You could still set initial conditions with different primordial patches that just so happen to annihilate and mix early enough so that you have the initial conditions right and you don't see the annihilation today. Would that be a possibility?
Well, but then if the annihilation happened early, I mean, you still, you still, either you annihilate everything, right?
Yeah.
And then you're down to the 10 to minus 18 that we derived.
So it's unthinkable to say, like, let's say you have different fields decaying in different ways and having different abundances of matter and antimatter, and that these averages to an offset. So this is not...
No, this is possible, right? This we'll talk about in a second. But I think the question here was, could it be that spatially, in some regions of the universe, right, you have matter domination and in other today, right? And in other regions you have antimatter domination.
All right.
And we would kind of today obviously be living in a region of matter domination. And is that possible, right? And then the issue is that if that is the case today, then there would need to be boundary regions. And those boundary regions need to be either completely empty, right, which we would see in large-scale structure, or they would have to give us some annihilation signal.
Yeah, I'll ask you later, but okay.
Okay.
Thanks.
More questions?
Okay. So then, what is the status in the standard model? So in the standard model, actually, we have all of these three conditions satisfied. However, so we get an asymmetry in the standard model. However, it's simply not quantitatively not sufficient to get the right number. So we do have baryon number violation in the standard model, not at the classical level. At the classical level, the standard model Lagrangian is invariant on the U1 baryon. However, the baryon number and also the lepton number, and more specifically the sum of baryon plus lepton number, is violated via the anomaly of the weak processes. And that gives us, hence, a small violation of baryon plus lepton number. We also have C and CP violation, right? This is something we have actually observed in the lab for weak interactions. And we have departure from thermal equilibrium simply because we live in an expanding universe. Things freeze out, right, as we learned, right? So we do have processes which generate something which is departure from thermal equilibrium. However, again, it's all, if we take all of this together and we compute the amount of baryon asymmetry that we can generate within the standard model, we simply get a number which is insufficient. So that means at this point, we know we need new physics. And we also know, I think, that, or at least there's no serious other suggestion, that this actually needs to be new particle physics. Yeah, you cannot really solve this by, I don't know, playing around with gravity or something else, right? We need new particle physics. We need to extend the standard model in order to have processes which generate this type of asymmetry. And then similar to the dark matter problem, you don't necessarily kind of have to add one particle, which is all its properties, right? You can also kind of modify things in a different way, so that you modify the cosmology and all this, right? So that you can enhance these three different aspects within the standard model, but you always need to add new physics somewhere. So this is why this is a very kind of interesting problem to think about, because it may be giving us a lead on how to extend the standard model. So let's look at a couple of famous examples, just to see how the idea works, and then I'll tell you about some more new ideas, though the new ideas are sometimes old ideas that had just been forgotten a bit and revived more recently. Or rather, I think you have a new idea. You give a talk and then somebody tells you, we discovered this in the 60s. This does happen. Or you read a paper which you don't understand, and then you do it all yourself, and after you've understood everything, you're back to the original paper and you realize that they were doing exactly what you were doing. This also happens. Okay, so maybe the most famous example, also one of the first examples proposed, is baryogenesis and grand unified theories. So the idea is we have some heavy particle which belongs to the gut system, right? So this could be a heavy Higgs or a heavy gauge boson associated with SU5 or with SO10, and this decays into standard model particles. Okay, we need to generate it somehow, but we're going to start at very high temperatures, close to the gut scale, so we can generate this guy. And then it decays. The decay can be arranged in such a way that it violates CP. This is pretty easy if it's a decays to some sort of Yukawa coupling where you have complex phases, then you can get the CP violation. And it also, very commonly in gut models, it automatically violates baryon number. So then kind of these conditions 1 and 2, they are already fulfilled automatically. So the only thing we need to worry about is the out of equilibrium decay. And for the out of equilibrium, again, we can now again rely on the standard freeze-out scenario, right? So we have, yeah, I mean, maybe I can just do this even graphically. So for the third condition, basically the point is that the number density of this X guy, right? You have the equilibrium number density, and then at some point you will have some freeze out, right? And the point is that now if this freeze out occurs earlier, I mean here this suppression, right, comes from the mass of the guy, and if this freeze out occurs before you get too much suppression from the boson suppression from the mass tail, right? Then you can have here an overabundance of the actual abundance with respect to the equilibrium abundance, while still having a large number density, right? So you'll always get a departure from thermal equilibrium here, but the point is that you want a departure from thermal equilibrium at a point in time where you actually still have enough of these particles left, because otherwise you're just not going to get a sufficient amount of asymmetry, right? If we have some process which freezes out down here, right, when we already have 20 orders of magnitude suppression in a number density, then that's just not going to be enough to give us a significant asymmetry. So the condition that you need is that you want freeze out, so gamma x, the decay rate of x should be Hubble at temperatures around or just above the mass scale of the guy, to avoid a too strong exponential suppression of the number density. And that just puts now again, you use the formula for the Hubble, right? A temperature squared divided by m Planck. And you plug in this, and then that gives you the condition that the mass should be some roughly bigger than maybe some order 1 factor times the decay rate m Planck, right? I mean, this is very similar to kind of the WIMP miracle argument, right? Just now we're not putting in at the electroweak scale. Right now we're working kind of at much higher scales, at the gut scale. So then you can just check in your gut model if this condition is actually fulfilled. And it's not difficult to fulfill, right? So in gut models, you can have particles pretty easily which do this, which means you've satisfied all 3 Sakharov conditions with relatively little effort, and it nearly automatically came out of your gut model, right? This is why was a kind of a very nice way how to kind of explain the Baryon symmetry, and nicely it also points to grand unified theory. Very nice, because we like those a lot, right? And everybody was happy. But then it was realized that one has to be more careful. And the reason is that this decay that you typically have in gut theories, it does violate baryon number, but more precisely what it typically, wait, I think I actually have this here, don't have to write it. It typically, it violates B plus L asymmetry. So it doesn't always have to be the case. In SU5, it's always like that. In SU5, the only thing you can violate is B plus L. In SO10, you have more freedom, and you can construct models in a way that they violate something else, and not just the linear combination B plus L. But typically, what you violate is B plus L. And then the issue is that you have these Svalaron transitions in the standard model, the ones we mentioned on the previous slide. And hence, while you do generate a B plus L asymmetry at very high scales through this gut mechanism, you will then, via the standard model B plus L processes, you will erase that again, right? Because basically, later, then the B plus L violating processes come into equilibrium, and then we violated our Sakharov condition, and we wash out, we erase all the initial asymmetry that we generated. So you can write a Boltzmann equation where you just say, okay, so I did generate some number density, some B plus L number density, but now once this Faleron rate becomes efficient, my number density is depleted not only through the standard Hubble expansion, that would be okay, but also explicitly through this violation rate, right? And if that is efficient, this thing just goes into equilibrium, so n dot equals 0, and you can see the solution to this equation is just that the final asymmetry is 0. So that was really a bit of a showstopper for gut baryogenesis. It's not that you can't do it, but the thing that it kind of just nicely and automatically falls out of the theory, that unfortunately was realized it is not the case. So that then motivated to look at a different type of baryogenesis models, and they go by the name of leptogenesis. So the idea behind leptogenesis is that you generate the asymmetry first in the lepton sector, and then you use this B plus L violating process, these Falerons, to precisely convert the initial asymmetry in the baryon sector, the initial asymmetry from the lepton sector into the baryon sector. So instead of being a showstopper, here they are really part of the model. So the idea is that, okay, let's introduce right-handed neutrinos. Right-handed neutrinos are very nice because we need them kind of anyway to give masses to the light neutrinos, right, via a seesaw formula. So we introduce these right-hand neutrinos NR. This is Yukawa coupling. This is the coupling to the lepton and Higgs doublet. This is a mass term for the right-hand neutrinos. So that the new parameters that we're adding are the mass term and the Yukawa coupling, but they're not completely free because via the seesaw formula they have to be linked to the light neutrino masses. Okay, so let's say we do this just because we want to explain light neutrino masses. Now, what does this mean for leptogenesis? So this process, which is mediated by this guy, so the right-hand neutrino going into lepton Higgs doublet via the Yukawa coupling, this can violate lepton number. In particular, you can have, do I have it here? No. You can have the process, so lepton Higgs via right-hand neutrino going into anti-lepton anti-Higgs, right? So this is, here you have lepton number +1, here you have lepton number -1. So here you have a process which is directly encoded already 3 level in this Lagrangian, which violates lepton number by 2 units. So that then together with the Svalerons gives you the baryon number violation. Then the CP violation, again, you do similar as we did for the gut baryogenesis. You use the complex phases in this Yukawa interaction. So this process also automatically violates, or it generically violates CP unless you put some very special parameters that are purely real. And you also can, again, very similar to the gut baryogenesis, you can get out of equilibrium decay by simply having the neutrinos decouple, or basically by the freeze out of the right-wave neutrinos, via the same mechanism that we discussed for gut baryogenesis. That also means that there's kind of constraints. For example, the ratio between the Yukawa coupling and the mass, right, is constrained by the light neutrino masses. Now, the fact that you need a sufficient amount of CP violation, a CP violation here comes, yes, it comes through the complex phases, but when you actually compute it, it comes from an interference of the tree-level diagram and a loop-level diagram. So not only the Yukawa couplings matter, but also the mass of the right-wave neutrino, which runs in a loop. And so that gives you a lower bound on the mass, the Davidson-Ibarra mass bound. And the fact, again, that you want to decay out of equilibrium means you can't make a Yukawa coupling too big, right? Otherwise, you'll be tracing the equilibrium density for too long, and you'll suppress your number density too far before freeze out. So that means you have several constraints on the model, because you have this constraint, and this constraint, so it's not obvious that it would actually work. But the kind of the magic bit of leptogenesis is that it actually works basically out of the box. So the standard leptogenesis story is that, okay, you go to relatively high temperature, you have right-wave neutrino masses of the order of 10 to the 10 GeV, you have Yukawa couplings of the order 10 to minus 3, which is kind of a reasonable ballpark if you look at what we have for the standard model Yukawa couplings. You have the lepton number violation via specifically this diagram there, and you have the out of equilibrium right-wave neutrino decay just from freeze out, and you plug everything together and you more or less get the right number. So this is a kind of very minimalistic and simple way to get the right number. The big disadvantage, if you want, is that you're not going to test that in a collider. And there's basically no signature that you can look for in this simple model. So it works, it may be the answer, but how will we ever know that that's actually the answer, right? And that's maybe the main motivation why people have continued to think very hard if there's also maybe other ways to do it. And maybe by basically excluding all the other possibilities or finding something, right? We can then get more or less confident that this may or may not actually be the way nature is working. So one way that you can basically stay in the same framework but push this to more observable scales is you can say, okay, well, this formula contains the ratio, right, of the Yukawa coupling and the masses. And it's actually not just that, but actually, if in reality, this is a matrix equation, right, because you have 3 active neutrinos, potentially 3 right-wave neutrinos, so you can actually you can have cancellations in this matrix equation. And this allows you to actually push the mass scale a lot lower. So we can have this mass scale down to GeV even, at the price of having some cancellations in this mass matrix, which means that we have some of the right-wave neutrino masses will be extremely degenerate, right? Meaning we have like a GeV scale and then maybe an EV mass splitting or something like that. You can say this is very fine-tuned, right? Maybe it is. Maybe there's a symmetry, but it's, at least in the equations, it is a possibility. Now, in this case, because you have these very low energetic neutrinos, you tend to, at freeze-out, be in the limit where they're actually still relativistic. So you cannot use the standard freeze-out computation to get anything out of equilibrium. So instead, what happens is that you get the out of equilibrium from the oscillations, because small mass splittings, as you know from active neutrinos, right? Small mass splittings means oscillations. So here you have oscillations among the heavy neutrinos and oscillations of the heavy with the light neutrinos. And then because you are in the ultra-relativistic regime, you don't really distinguish between neutrinos and antineutrinos, even for the heavy guys. But what happens is that at the electric phase transition, which is when these Faleron processes stop to become efficient, you have some of your lepton number in the right-hand neutrinos, some of the lepton number in the left-hand neutrinos. But the Svalleron processes are strictly just SU2L processes. So they only pick up the part of the neutrino, the part of the symmetry, which is in the active neutrinos. So the way you violate lepton number here is a bit more subtle, right? You're not actually working with this decay diagram over there, or with the scattering diagram. You're really just having oscillations. And then at the time when you measure your lepton asymmetry, your probe of measuring the lepton asymmetry, meaning your Svalleron processes, only take into account the particles which are charged on the SU2L, and hence they only measure these guys. And now if the symmetry is or if your energy density is distributed simply over both the right-handed and the left-handed guys, but your probe only measures one of them, then this is how you produce an asymmetry in the baryon number, which is what was your initial goal. Are there questions so far? So both for the gut baryogenesis and the leptogenesis.
How are imaginary couplings to be understood physically? Like, what does it mean to have an imaginary coupling?
Well, it basically means that you have a CP violation. I mean, a priori, it's just. I mean, a priori, it's just you have the Yukawa coupling, right? Which in this case is a 3x3 matrix, right? And okay, if you just have kind of one particle, right, decaying into something, right, then you could always, and you have Yukawa coupling, you can always rotate that phase away, right? And this is why that phase never shows up, right? If we just write down a very simple toy model of whatever, a single fermion, a single boson, or something like that. The issue is if you have states where the system is sufficiently complicated that the mass eigenstates are not the flavor eigenstates. Then you cannot just rotate everything away, right? And then you're left with these complex numbers.
I have a naive question, because I'm a bit confused with these two diagrams. I mean, I thought that the main process bringing the thing out of equilibrium was the decay. That actually the scattering was your enemy, because this is what tends to wash out the symmetry that you create in the first place.
Right. So this is that diagram is not what gets you out of equilibrium. That diagram is what gives you the lepton number violation.
Okay.
Well, I mean, if you cut it in half, right, it's the decay.
Yeah.
So it depends. You can do it both thermally and non-thermally, right? Mm-hmm. If you do it, so actually, kind of this simple picture of the I mean, you can have departure from thermal equilibrium at 2 points here. Where's I've lost the only pen that actually writes. It's okay. So here you get departure from equilibrium here. But you also get departure from, if you say I start from initial abundance for the right-hand neutrinos, right? Meaning your starting point is somewhere here, right? And then you first have to build up. You will also get departure from thermal equilibrium here. And now it depends on what is your initial condition, right? So you can do leptogenesis where you assume kind of you have the heavy guys, right? Maybe they come from some inflaton decay or something, right? Then you will be starting up here. And then you basically have to get the departure from thermal equilibrium down here. Or if you start with 0 initial conditions, you can have it also here. And then depending on the parameters of the theory, either this is more dominant or this is more dominant. But yeah, but this is the thing. You have to, I mean, you need this departure from thermal equilibrium, right? So if this process is extremely efficient, then you're just tracking the equilibrium number density, right? But in any case, at both ends, at some point you will have a deviation. But the point is you want to have the deviation at a point where you actually still have right-hand neutrinos, right? If I have the deviation down here when I've already lost 20 orders of magnitude in my exponential tail, then I'm not going to get enough baryon symmetry. Okay, in the remaining few minutes, I just want to briefly talk about some more modern ideas, right? Though, as I say, modern can also mean actually very ancient but rediscovered. So one is this is still a rather classic idea, is electroweak baryogenesis. So here, I mean, this was motivated a lot by supersymmetry, but I think it's still an interesting, and so it's gotten maybe a little bit less interesting with the LHC not finding a clear hint for supersymmetry. But I still think it's a very instructive model, and there is definitely still ways that this could still be realized. So the idea is that the electroweak phase transition, as measured in the standard model with the parameters of the standard model as measured, is a crossover phase transition. Crossover means it's a relatively smooth process, which means it doesn't give us a lot of departure from thermal equilibrium. However, if you extend the standard model, and particularly you extend the Higgs sector, you can make the electric phase transition first order. And that gives you simply a stronger departure from thermal equilibrium. And then that by itself is already sufficient without having to modify any of the other Sakharov conditions, that actually gives you enough departure from thermal equilibrium to give you the enough baryon symmetry at the end. So the details are complicated, right? You need to kind of think about how does the electric phase transition happen, how do these bubbles form, what happens at the bubble wall, what happens with the sphalerons, right? The details are complicated, but the key idea is that. Another idea that is actually pretty elegant is so-called spontaneous baryogenesis. So here, the idea is you introduce an extra particle, an extra field, which is an axion-like field. It doesn't have to be the QCD axion, it can be the QCD axion, but it's something which couples via a derivative coupling. So theta is my new field, and it couples via a derivative coupling to the currents. So here I've written a direct coupling to, say, baryon or lepton current. And now the idea, and this is a term that I can write in the Lagrangian because I mean this is basically the same term that appears in an axion model, right? In an axion model, this would just be the fermion current, and this would be the coupling of the axion to the fermions. So you can, and this is kind of allowed by all symmetries of the theory. This is shift symmetric, nice fit for the axions. And now what I can do partial integration. I can take this derivative acting on the theta, right? So now I have theta dot. I only have the theta dot. I don't have the spatial derivatives because I'm going to be assuming some homogeneous but rolling field in the universe. And then I couple here to the zero component of the current, which is nothing else than a charge. Okay, but this term here, kind of now coupling the charge to something. This is nothing else than how you generate a chemical potential. So if in your Lagrangian you have a term where you're coupling you have the charge with some factor in front, then this factor in front is nothing else than a chemical potential. This is how you write a chemical potential into your Lagrangian if you do thermodynamics, right? Or if you do Legendre transformations. So the interpretation is that a rolling axion-like field acts as a chemical potential, meaning it makes it more easy if I now simply have some thermal bath, the thermal abundances in this thermal bath will be different for particles and antiparticles by this effective chemical potential theta dot. Oops, that was too fast. And that's all I need, right? That now I can basically, and the interesting thing is, I don't need any additional departure from thermal equilibrium, right? This is all I need. And you can say, okay, this rolling theta dot is probably not the global thermal equilibrium of my global theory, right? I'm somehow not in the global minimum of my theory, but locally I am in thermal equilibrium, right? All my particle interaction rates can be in thermal equilibrium. The only thing that I need is that that I have some slowly rolling field, which could be the axion or could be something else, and that kind of distorts the energy levels of my theory, and this way I can generate a lepton asymmetry or baryon asymmetry. Theta dot is non-zero. Oh, yeah, no, non-zero, very important, yeah. Sorry, yeah. And so here I wrote directly a coupling to the baryon or lepton current, right? Because then you see you directly generate a chemical potential for baryon number or lepton number. If you do it for lepton number, then as with leptogenesis, then you need to use the sphalerons to get it to baryon number. If you just couple directly to baryon number, you're done. Actually, the mechanism is even much more general because you can couple to nearly whatever you want. You can even couple to things that are not charged on a baryon number or lepton number. because now you're inducing some sort of chemical potentials into your plasma of the standard model. And now you have all the interactions of the standard model, right? So even if the thing that you couple to, so say I couple to GG dual, right? Then that would a priori, that is not charged at all on the baryon number. But I mean, now I'm coupling to all the quarks, right? And you have all the Yukawa interactions in the quarks, and they will eventually, transfer the symmetry into some particle species which does carry baryon number. So this is actually a very, very general mechanism. As soon as you have some sort of rolling axion-like field in the early universe, which has somehow coupled to the standard model thermal bath, this does tend to give you an asymmetry. Then the question is kind of how long does this field roll, right? Because as soon as this field stops rolling, you have nothing more kind of pumping the asymmetry between particles and antiparticles, right? So you need to make sure that your asymmetry freezes out before this field stops rolling. That's the condition you need to meet. Okay, similarly, Affleck-Dime barogenesis is kind of one more complication on top, right? The complication on top is that here we thought, okay, this field theta is a fundamental field in the sense that we think of it as a phase of the axion, or the phase of the Pechi-Quinn field, right? Or the axion on axion-like particle. Now, this field theta could also be a composite field. And in particular, in supersymmetry, you have what is called flat directions. So these are directions which are not charged under any gauge symmetry, and hence when you compute the scalar potential in supersymmetry, they are very flat in field space, which means you can easily sustain some long rolling period, which is exactly what you need, right? So then once you've identified what is theta, which is some condensate of quarks and leptons, then once you call this condensate as kind of one effective field, then the mechanism is basically the same as spontaneous barogenesis. But this is a way to kind of actually, so you can either add something like an axion-like field, or you can add supersymmetry, depending on your preference, right? And in both cases, you can get this to work pretty neatly. Then finally, a relatively different idea is that you could also, so far we've talked about generating the asymmetry always in some particle versus antiparticle, but the Sakharov conditions never actually said anything specifically about particles and antiparticles, right? They just made statements about violation of symmetries. And you can violate these symmetries without actually introducing particles or new particles. So one way is if you had primordial helical magnetic fields. So this means I have, by some mechanism, right, to be discussed, right? By some mechanism, you manage to generate large-scale magnetic fields in the universe, where one polarization is enhanced with respect to the other polarization. This is the meaning of the word helical. Now you violated CP, because I have now a universe filled with magnetic fields of different helicity. Okay, so you violated CP by putting these magnetic fields, or by generating these magnetic fields. You violated thermal equilibrium, because the thermal equilibrium condition of the universe would be to have zero magnetic fields everywhere. And now what you need is baryon number violation. And this we can now again use the Sphaleron processes at the electric phase transition. Because what happens is that in the standard model chiral anomaly, the coupling of the hypermagnetic field to the anomaly is different than the coupling of the electromagnetic fields to the anomaly. So when you go to the smooth electroweak crossover phase transition, your hypermagnetic fields get converted into electromagnetic fields, and this mismatch has to go somewhere, and this mismatch goes into the anomaly, and the anomaly is precisely the B plus L anomaly. So just the conversion of hypermagnetic fields into electromagnetic fields generates a baryon asymmetry through the sphalerons. So this is just, I give this as an example, how you can actually, now you still need to discuss how do I generate my helical magnetic fields, right? And there are models that do that, but this is, and some of them actually go back to introducing these types of fields, right? But this is just an example to show you that Sakharov conditions don't actually say I need a heavy particle which decays violating baryon number. You don't, right? The Sakharov conditions are phrased in a very general way, and there's a good reason why they're phrased in this very general way. Okay, I have one very last point, and then I'm done. And that is, we talked previously that we have to be careful if we get too close to the equilibrium condition, we have these washout processes, right? So meaning we get driven, our actual number density gets driven back to the equilibrium number density, and then we cannot fulfill Sakharov conditions, and we cannot generate a Barron symmetry. Here we have a mechanism which actually profits from thermal equilibrium. And the idea is, it's a bit similar to here, right? So here again, you say somehow, primordially, I generate some asymmetries in my standard model particles, which, however, do not yet violate B minus L. So for example, I could do gut baryogenesis, right? Gut baryogenesis generates asymmetries, right? The problem is just that it generates the asymmetries in a B plus L, and then we learned that B plus L we cannot conserve because we have the spherical ones which will wash it out. So let's say we have gut baryogenesis, we generate asymmetries which only violate B plus L but not B minus L. But now we have the right-hand neutrinos, let's say with a very large Yukawa coupling so that they're completely thermalized. What the right-hand neutrinos do is they erase lepton number. But if we start with a B plus L asymmetry, now we erase all the lepton number out of it via the right-hand neutrinos, then what we're left with is just a Barron asymmetry. And that's exactly what we wanted to do, right? So I'm giving you these different examples, and this is the end of the list, just to show you that there's really different ways how to think about this, right? You kind of, at the end, you always need to fulfill the Sakharov conditions one way or another, but you can do it in fairly different ways. And as soon as you have some sort of model which gives you some sort of CP violation, this is kind of different ways that you can think about it in order to check if it does something interesting for baryogenesis. Okay, thank you. Excellent.
Hi, thanks for the nice talk. I have a question about actually like signatures from all these models, because I don't know about many, but for example, from people doing electroweak phase transition, what they tell me is that usually you have to choose if you want gravitational waves in the range of LISA or if you want baryogenesis. So like, I had to choose if I want something that works or something that I can see. I don't know about the others, if they have something more typical that we can actually distinguish outside of collider physics, of
yeah,
course.
very good. Yeah, unfortunately, that's kind of true. It's annoying that it's kind of true because both for the electric baryogenesis, what you need is a first order phase transition, right? And also to get a strong gravitational wave signal, you need a strong first order phase transition. So naively, you would kind of think that that's the same part of the parameter space that you're probing. But then if you go into the details and you actually like compute benchmark models, right? Indeed, like there is some overlap space, right? So there is some models that you could probe with LISA, and that would actually give you successful baryogenesis, but you cannot, like a non-observation of gravitational waves at LISA will not rule out electric baryogenesis. But since electric baryogenesis is kind of happening at the electric scale, I think, you know, in the end, right, when we have Higgs precision measurements, maybe with the FCC or something, I think we will get there. The low-scale leptogenesis model with the neutrino oscillations, that is basically constructed to be observable. So there you can look at heavy neutral lepton decays in like facilities like SHIP or Phaser, and that there you can probe maybe not the entire parameter space, but you can really probe large chunks of the parameter space. With these other models, it depends, right? So for example, here with the magnetic fields, you could then go and you could look actually for the remnant magnetic fields in the universe, right? And this is something that we do, and we have some hints for magnetic fields in the universe, right? But with these Blazer observations, right? But it's a bit unclear what exactly is the status. Regarding these types of models, it depends, right? Because this is a very general idea. So there are realizations of this model, in particular if you do this with the QCD axion, then it becomes very testable. But if you just say, okay, this is some pseudoscalar field and it can operate at very high energies, right? Then again, okay, in some cases you can hope for a gravitational wave signal, but in some cases not. But I would say all of these models have at least some way to probe them, whereas standard high-scale leptogenesis, despite I think my theory bias is still that I think that's the most beautiful model, right? Unfortunately, that's kind of really close to impossible to probe.
Thanks for the lecture. I have a very naive question. During the whole talk, you were talking mainly about baryon asymmetry, but also we know that the electron number density is almost the same as a proton number density. So I wonder, this is appear just from electric charge conservation, or we should also keep track of lepton asymmetry?
That's actually an excellent question. So we know, we know that we have charge neutrality in the universe, right? Because if we did not, right, we would notice kind of charged things just flying off towards, I don't know, some galaxy, right? Exactly. So we know that the number of electrons has to match the number of protons. However, there could still be a very large lepton asymmetry, which could be in the neutrinos. Because in fact, what we measure, say with BBN, right? When we say, okay, we look at a neutron freeze out and all this and a neutron abundance, we really just measure. We measure, strictly speaking, what we measure there is actually the abundance of electrons. And then because of charge neutrality, right? Then we say, okay, this is the abundance of protons, and hence this is the abundance of nucleons. But the neutrinos, there could be a significant neutrino symmetry. And indeed, the most stringent bound, again, comes from BBN, because neutrinos also play a role in BBN. But the bound is much, much weaker, right? So the bound on the Brown asymmetry is 10 to minus 10. The bound on the lepton asymmetry, if it's in neutrinos, is about 0.1. So there could be a huge lepton asymmetry, nearly order 1 in our universe, and we wouldn't know.
Thank you.
One last question.
Hi, thank you for the nice talk. So I was asking that in effective field theory, the dimension 5 Weinberg operator, it violates lepton number by 2. So is there any other higher dimensional operator that violates B plus L symmetry?
Okay, so the Weinberg operator actually violates B minus L, right? Yeah. And that's actually basically integrating out this process, right? Gives you the Weinberg operator. Now for B plus L, I mean, okay, yes, we can write down higher dimensional operators, right? But the thing is, we already have the Sphaleron process, right? And the Sphaleron process, I mean, so the Sphaleron process is a non-perturbative process, which is kind of why we don't phrase it in terms of high dimensional operator, right? It's going from in kind of the vacuum of the SU2 left vacuum, right? It's a process involving actually 12 quarks and leptons but it goes from one vacuum, kind of one Chern-Simons number to another Chern-Simons number, thereby violating B plus L. And so and since that's already in the standard model, we can't get rid of it, right? That's the dominant process.
Okay, thank you.
Okay, thank you, Valerie. Let's move on to, let's thank her again. And,
Okay, very good. So welcome back to the second set of dark matter lectures. So yesterday we talked about cosmological constraints on dark matter, especially and some of the especially theoretically motivated areas, especially the thermorelic framework. So just to sort of sketch something that I showed as a cartoon yesterday, we talked about how if we look at the dark matter mass, if we think of the parameter space in terms of the dark matter mass and interaction strength, we've talked about how cosmological constraints tell us that the dark matter can't be lighter than about 10 to the minus 21 eV. Yeah, what do we want? Good. And we've talked about how at the other end there are potential constraints on very heavy dark matter from gravitational lensing and similar observations. We talked about how cosmic constraints from the cosmic microwave background basically say that the dark matter can't scatter too much with standard model particles, lest it disrupt the CMB. And then, so we've talked about, and we talked about some sort of target regions in this space. In particular, so that if this is around the keV scale, then in this region down here, the dark matter has to be a cold non-thermal bosonic field, and then we sort of mapped out this thermal target region. So this is not ruled out. This is theoretically interesting region in which extends up to mass scales around 100 TeV. We said that there are BBN constraints at the MeV scale and down, which constrain this, which sort of constrain this thermal window, and between about an MeV and 100 TeV, there's this thermal window in which dark matter was once in thermal equilibrium with the standard model, and that provides a particular target region. And within this region, there's sort of this narrower classic WIMP region that's been the subject of a lot of testing. So that's kind of my, so what I'm going to talk about in this first lecture is constraints beyond cosmology and astrophysics, so constraints by dedicated terrestrial experiments and by accelerators that allow us to start carving deeper into this parameter space than we can do with the cosmic bounds alone. So I gave you I gave you a little cartoon last time, which was sort of like, all right, we have some bounds like this, already ruled out by direct detection and indirect detection searches. Francesco Colore's lectures over the next few days are going to talk about indirect detection, but in this first lecture this morning, we're going to focus on the direct detection side of things. In the second lecture, after the coffee break, I'm going to talk a bit about the QCD axion window at low masses, which is another theoretically motivated target to go after, and then I'm going to talk about some of the progress that has been made in axion search experiments, which currently probe the QCD axion over some of its band, but over the next 10 years sort of have the possibility to probe the QCD axion and many other related properties over a much larger range. So that's the framework for the lectures today. We'll mostly be focusing on terrestrial searches with a bit of discussion of the cosmology and models for the QCD axion. And at the very start, I want to finish the last thing that I didn't say last time, which is the freeze-in cosmology, which is an alternate benchmark for this particle ITM case. Okay. Now I shall move the board out of the way. All right, so that cartoon given, let's begin. So left over from yesterday, I just want to briefly discuss the freeze-in benchmark, which is an alternative way to get the correct abundance of dark matter through its interactions with the standard model. Then we'll move on to searches and talk about the signal calculation for classic direct detection. There's been a lot of work in the last 10 years or so to go beyond the classic direct detection approach of looking for recoiling nuclei from dark matter particles scattering with those nuclei. So I want to talk briefly about that, although a lot of what I'll be doing here is pointing you to references if you want to learn more. And then I want to say a bit about searches for dark matter and for dark sectors at accelerators. So these can be the searches for the dark matter itself or for particles that interact with the dark matter, such as the vector or scalar mediators that we talked about last time. So I'll say a bit about both the classic searches at the LHC, the searches using lower energy accelerators, and the searches that don't look for the dark matter at all, but just try to go after the mediators. All right, but to begin, we talked about the thermal relic benchmark in quite a lot of detail about the freeze-out scenario, and we talked about some variations to the freeze-out scenario where the annihilation rate is suppressed or enhanced at late times, where the scaling goes with something other than the density squared of dark matter, and this modifies the mass window that you get for freeze-out. But one other important benchmark is freeze-in, which evades constraints from Big Bang nucleosynthesis by simply saying, okay, well, what if the dark matter never got into thermal equilibrium with the standard model in the first place? So the basic picture here is that is to ask, all right, dark matter may, if there are some interactions between dark matter and the standard model, they will gradually equilibrate with each other. But what happens if that process never completes? So the picture here is the initial abundance of dark matter coming out of inflation is negligible, but then either dark matter or something that will decay producing dark matter is produced with an abundance much smaller than equilibrium through rare interactions with the standard model path. So here you start out with nothing, the interactions start to slowly populate the dark matter over time, and in the epoch when the temperature of the universe is larger than the dark matter mass, so there's no kinematic barrier. So, this little sketch over here, the black line is the standard freeze-out scenario that we talked about last time, where you start with some high abundance, it gets depleted through interactions with the standard model, and eventually you hit this plateau. The freeze-in scenario is schematically sketched by these colored dashed lines, where you start out with very little, rare interactions with the standard model start to populate the dark matter, drive it towards this thermal equilibrium line. But eventually, typically when the temperature of the universe drops below the mass of the dark matter, these production processes become inefficient just because you don't have the energy to make the dark matter anymore. So if the production rate rises with decreasing temperature, which is a somewhat generic behavior, then, hang on, did I say that the right way around? Then most of the dark matter will actually be produced by interactions near the end of this process, so interactions occurring around T similar to M. So in that case, we'll retain this advantage of the freeze-out scenario, that the abundance is actually kind of insensitive to what's going on at really high energies, provided that you don't make too much dark matter early on. So for this kind of IR-dominated freeze-out, you want a situation where you don't produce very much dark matter in the early universe, the interactions become more important with time, but then they get cut off by kinematics. You can also have other variations of freeze-out where you do produce more of the dark matter in the UV. So because in this case, the interactions are never strong enough to bring the dark matter into thermal equilibrium, this typically requires much smaller couplings than freeze-out. Now, that's pretty unnatural if you want the dark matter to interact directly with, say, the W and Z bosons in the standard model, so this doesn't work very well for the WIMP scenario. But if we're talking about neutral vector or scalar mediators that have some tiny mixing with the Higgs boson or the standard model photon, then this can be a natural scenario. And perhaps somewhat surprisingly, these freeze-in models can still be detectable, especially if the mediator is sufficiently light. Well, so there are two ways in which they can be detectable. One is the kind of cosmological constraints that we talked about last time, and the other is by looking directly for the interactions. And the surprising thing is that direct detection with a light mediator is sensitive enough to actually get close to this freeze-in benchmark. Because you never make dark matter with the abundance of radiation in this case, those BBN bounds that we talked about can largely be evaded. Remember, the BBN bounds are telling us about extra radiation species, that this is never populated at the level of a radiation species. The abundance is always smaller than what it is in the present day. So that means that we can largely escape the BBN bound. So this is an example of a case where the BBN bounds on thermal dark matter don't really apply, but the warm dark matter bounds that we talked about that require the dark matter to not be fast moving, those can be relevant because the phase space distribution of these of dark matter produced in this way is in general not a fully thermal distribution because you're never fully equilibrated. So this is one of those cases where you have to take the phase space distribution into account carefully. This was done for some classic freeze-out models in this paper by Dworkin et al., and they find that the warm dark matter constraints basically test freeze-in models up to tens of keV. So this provides a way to populate populate dark matter through its interactions with the standard model at sub-MeV mass scales. Okay, so that's the freeze-in benchmark. That's another, sort of like another little section of theory-motivated space down here. All right, so let's now talk about how you search for this kind of thing or for the other benchmarks that we talked about. Again, there are many ways to do this. One of them is direct detection. The basic idea here is we're going to put sensitive dedicated detectors around a large volume of target material. We're going to bury it underground to reduce backgrounds. This There are some exceptions to this. Sometimes you want to put it on the surface. Sufficiently strongly interacting dark matter may not be able to get underground, and that can be a loophole for these things. And then we look for indications of nuclei recoiling with no apparent cause, and or other indications of energy being deposited onto the target material by dark matter particles interacting with it. If we can reliably shield out the other backgrounds, which is a difficult technical challenge, but one that current direct detection experiments have done a very good job of doing, then the cause must be something that can get through all our shielding, such as neutrinos or dark matter. We think we know what the background should be from solar neutrinos. That's called the neutrino fog. Current generation dark matter experiments are not yet at the point where your neutrinos are the major background. In 10 years, that story might change. So the hope then is that if we see a signal, that would be a sign of dark matter. This is a recent result from the LZ collaboration. So on the y-axis here, this is the effective WIMP nucleon scattering cross-section. We're going to talk a bit more about exactly how that's computed. This assumes a spin-independent cross-section. I could show similar results for spin-dependent. And on the y-axis, this is the WIMP mass. This axis is going from 10 GeV up to about 10 TeV. So this is very much this classic WIMP region that I talked about. And this is a great way to look for classic WIMPs. The cross-sections being probed here are down at the level of 10 to the minus 47 square centimeters, which are incredibly tiny cross-sections. These are some of the tiniest cross-sections we have ever probed in any context. All right, so what I want to do for the next part of the lecture is just talk a bit about, how this calculation works, what goes into it, why, what this y-axis actually means, and why there is this sharp decline in the constraints at low masses below about 10 GeV. Because this is a great way to look for classic WIMPs. It is a less great way to look for these portal models that often populate the space below the GeV scale. Okay, so the answer for that cutoff, let's look at that first, is really simple. It's just basic classical kinematics. So we're going to, if we imagine searching for nuclei of as Mn that are recoiling due to the scattering of a dark matter particle, which I'm going to label as having mass m chi here. So chi here means the dark matter, Sm means the standard model particle it's bouncing off, in this case a nucleon. Then the observable that we're going to look at is the rate of recoils as a function of their recoil energy, which I call ER. So we can work out the classical kinematics for this. So let's work in the lab frame to begin with. So in that frame, the nucleus is initially at rest, and then we have this dark matter particle with velocity v coming in, bouncing off the nucleus. We've all, I think, in our undergrads done many calculations like this. So this is just non-relativistic hard sphere scattering. So after the interaction, the nucleus will recoil at some angle theta. The dark matter particle will bounce off, and we can just write down the equations of conservation of energy and momentum. So where this is a non-relativistic process, we're going to, for the moment, assume that it's elastic scattering. You can get inelastic scattering, which allows for some energy to be stored in either the dark matter or the nucleus. But for the moment, let's ignore that and just assume that all we have to worry about is kinetic energy. In that case, we get this equation for energy conservation, and we get these two equations for the conservation of the x and y components of the momentum. So we'll do the algebra, which, again, I know we've all done many times as undergrads, to eliminate the velocity of the dark matter after the recoil and the recoil angle of the dark matter. And that gives us a result that looks like this for the recoil energy, where mu is the reduced mass of the system here. So the reduced mass of the system, where one of the particles is much lighter than the other, the reduced mass will just be the mass of the lighter particle. When they're comparable, the reduced mass will be of the same order. This gives us an expression for the recoil energy that looks like this. And again, this is in the lab frame. So it depends on the scattering angle. It scales with mu squared v squared, where v is the incoming velocity of the dark matter particle, and it scales with 1 over the mass of the nucleus. So we can already see from this that in the case where this reduced mass is controlled by the nucleon mass, so where the dark matter is much heavier than the nucleon, then this is just going to go like mn squared v squared divided by mn. So it's going to go like mn v squared. So in that case, the recoil energy is really just going to be determined by the mass of your nuclear target and how fast the dark matter is going in the halo. We think we know how fast the dark matter is going in the halo from observations of rotation curves. It's about 200 kilometers per second. So in that case, we have a prediction for this recoil energy, which is basically like v squared. Parametrically, it's v squared times the mass of your times the mass of the target. Now, in the other limit, though, where the dark matter is much lighter than the nucleus, then this reduced mass will be dominated by the dark matter mass, and the parametric scaling here will be the dark matter mass squared divided by the nuclear mass. So for dark matter that's significantly lighter than the nucleus, this recoil energy will be very suppressed. And that's basically why we have, that's basically why these classic direct detection experiments have trouble probing dark matter that is much lighter than atomic nuclei. So what we will predict here is that there will be a spectrum of recoils extending from 0 recoil energy up to some maximum recoil energy, which is just given by taking cos theta to be 1, which is parametrically given by this. So another way to say that is that at a given recoil energy, only dark matter particles with velocity higher than some minimum velocity can possibly contribute. So we can do some quick estimates for this. Let's suppose the target nucleus is around 10 to 100 GeV, so it's got 10 to 100 protons and neutrons. You can't really make atomic nuclei much lighter than the GeV scale for obvious reasons. Hydrogen's the lightest thing that we've got. And so if we take this limit where dark matter is similar mass or heavier, then we're in the regime where you're just dominated by the nuclear target properties. The velocity dispersion of dark matter locally is about 10 to the minus 3. So that tells you that in that regime, the typical recoil energies are going to be in the range of 10 to 100 keV. And so these large WIMP search experiments do an extremely good job of measuring recoils in the 10 to 100 keV scale. If the dark matter is significantly lighter than the nucleus, though, these recoil energies become much smaller. So if I've got a nuclear mass of 100 GeV, then if I've got a 1 GeV dark matter particle, my recoil energy is going to be only a tiny fraction of a keV, and that's unobservable in the classic nuclear recoil experiments. So for detecting light dark matter, the name of the game is you want to be able to measure very tiny energy depositions into your target material, and lighter targets help. Okay, so we'll talk more about that in a little bit, where we go into what are the new techniques that you need for lighter dark matter. But let's stick with the heavy dark matter case for a moment and work out, how we actually compute the nuclear recoil spectrum. So the ingredients. So again, what's observable in the end is the scattering rate as a function of energy. The ingredients that go into that. Well, first we need to know the amplitude for the scattering of the dark matter on individual nucleons. That's going to be a function, in principle, of the dark matter velocity and the recoil energy. So we have some particle physics here, which is how does the dark matter couple to quarks and gluons? That's going to depend on your dark matter model. And then we have the nuclear physics, which is what are the quarks inside the nucleon? What's the quark content? Once we have the amplitude for dark matter scattering on individual nucleons, we need to translate that into an amplitude for dark matter scattering on the whole nucleus. So there's some particle physics in this, because you have a question, okay, when you combine the amplitudes for scattering on different nucleons, do they add up coherently, or does something else happen? So this is a separation where, so this is why the cross-section limits often get separated into spin independent or spin dependent. In the spin independent case, the usual assumption is that the nucleon amplitudes just add up coherently. And so you get a scaling with the number of nuclei squared in your cross-section. On the other hand, if the amplitude is spin dependent, nucleons in targets typically exist in paired spin configurations, right? I have like a spin up one and a spin down one. So in that case, almost all the contributions from the different nucleons cancel out, and you're left with a result that is just proportional to the number of unpaired spins in the nucleus squared. So there's some particle physics here. Does the amplitude for scattering depend on the dark matter spin? Depend on the nucleon spin, yes or no? More generally, how does it depend on the nucleon properties? Does the dark matter couple equally to protons and neutrons? Again, this will be different between different dark matter models. If your dark matter, for example, is interacting through some mediator that is kinetically mixed with the photon, that means it couples to electric charge. That means it's going to want to couple to protons, not so much to neutrons. On the other hand, if you're coupling through, if you're coupling through the Higgs portal, for example, then your result will depend on the coupling of the Higgs to the standard model protons and neutrons. There's also a nuclear physics factor here, which is, the nucleus is of finite size. When a dark matter particle comes in and bounces off it, it doesn't necessarily see all the nucleons. That's typically parameterized with some kind of form factor. Finally, so now suppose you've done all that, you have your model, you've got your nuclear physics calculations, so now you have a scattering amplitude for dark matter to bounce off the whole atomic nucleus, then you need to convert that scattering amplitude into a scattering rate. And that will depend on the astrophysics, on how many dark matter particles you have around in your halo and the velocity distribution for the dark matter. So there are a bunch of simplifications that are made within the standard calculation. And a lot of the sort of non-trivial dark matter models, or like non-trivial signatures in these experiments, basically come from, what if we relax one of these assumptions? So the standard set of assumptions is that we can treat the scattering as a contact interaction set by some couplings we'll call Fn and Fp of the dark matter to protons and neutrons respectively. We're just going to write things in terms of like Fn and Fp. The standard case is to just assume that these are constants, independent of things like the momentum transfer or the scattering angle or the velocity. Now, there are models where those aren't true, where there is momentum dependence in the scattering cross-section, and so in that in those cases you need to take that into account. There's often a further assumption made that we can just take Fn to be equal to Fp. If that's not true, it matters when comparing the sensitivity of different targets to each other. Again, for the spin dependence, people typically consider two cases of spin-independent and spin-dependent interactions. This is just what I said before. This determines whether the nucleon amplitudes add coherently, in which case you get an overall rate scaling as atomic mass squared, or whether the amplitudes from paired nucleons cancel out, in which case the overall rate just scales as net spin squared, and thus you tend to get much smaller rates in the second case. The form factor describes the momentum dependence of the interaction due to the finite size of the nucleus. The standard calculation just uses a simple parameterization called the Helm form factor. I'm not going to go into detail on that, but come talk to me if you want to know more about form factors. And for the velocity distribution in the standard calculation, there's usually just an assumption that there is some Maxwellian distribution, and sometimes with some kind of cutoff for the escape velocity of the galaxy. Yeah, I guess I will say the other problem with the energy recoil stuff, you might say, oh, well, you know, that if the dark matter has sufficiently high velocity, you would still be able to see a signal, right? Even if the dark matter is light. And that's true, but sufficiently high velocity dark matter becomes unbound to our galaxy, and so doesn't stick around for a long time. Although there are some suggestions for using direct detection experiments with dark matter that has been accelerated in some way and thus doesn't need to be bound to our galaxy, in which case you could have sensitivity to light or dark matter. So yeah, this is just the point before that many non-standard dark matter models work by basically relaxing one or more of these assumptions, and that can substantially change how you compare sensitivity between different experiments. But whenever you see that standard plot of dark matter nucleon scattering cross-section versus mass and the constraints on that across different target materials, this is typically the set of assumptions that is going into it. Okay, so let's just go ahead and see how that standard calculation works out. If we switch to the center of momentum frame, we'll let the scattering angle be labeled theta, and we're going to work in simple models in which we can treat the rate as just being independent of the scattering angle in the center of momentum frame. So again, we'll do our same, momentum transfer calculation. So in this case, we have the scattering angle theta for the nucleus. This is the thing that we can actually observe. We can write down the 3 momentum transfer Q. This is going to, as previously, this is going to tell us about the reduced mass of the system, the relative velocity of the particles, and the scattering angle. So we can write the thing that we're actually going to measure in the lab typically is the recoil energy in the frame of the nucleon. We can express that lab frame recoil energy, which we worked out before, in terms of this momentum transfer. So this was the thing that we calculated earlier. We can write this in terms of Q squared and 2mn. So we can write the rate of events at a given, so we can see that this recoil energy is just directly related to the scattering angle. We can write the rate of events at a given recoil energy just in terms of the rate of events at a given scattering angle in the center of mass frame. So this is our observable. It's our first step. So if we want to predict this, we need to know just how the rate varies with scattering angle in the center of mass frame. Okay, so now this result is directly related to what we usually compute from Feynman diagrams. let's make some more of those assumptions. Let's look at spin-independent scattering for the moment. So we'll take contributions from different nuclei to add coherently. So this is our step to get the nuclear matrix element that we talked about before. As I said, there'll be some form factor out the front. This is just tracking the momentum, the dependence on the transferred momentum that comes from the fact that the nucleus has finite size. So particles coming in, particles exchanging a different amount of momentum c, different fractions of the nucleus. So that'll be our form factor prescription, and then we're just going to treat the matrix elements as being a matrix element for proton scattering, a matrix element for neutron scattering, and then they just add up coherently with prefactors that are determined by the number of protons and the number of neutrons in the nucleus. So the cross-section in the center of mass frame can be related to this nuclear matrix element just by this result. This is sort of our standard expression for 2-to-2 scattering, relating the cross-section to the scattering amplitude. And then to convert from the cross-section to the rate, we need to know how many dark matter particles there are and how fast they're going, and the conversion factor for that looks like this. So we'll assume, if we assume that there's no dependence coming from that there's no dependence on the angle phi in this calculation, so we can trivially integrate over the possible, so this is like the azimuthal angle in the scattering, then we can write so we previously wrote the rate as a function of recoil energy in terms of the differential rate with respect to solid angle in the center of mass frame. We can convert that into the differential cross-section with respect to solid angle multiplied by some factors that come from the astrophysics, and then with this prescription for the nuclear matrix element, we can write the result. We can write the result like this. So here's our form factor. Here's our nuclear matrix elements that are going to come out of the particle physics with our coherence assumption, and here's a bunch of astrophysical factors that allow us to get the overall rate. So here we've written this in terms of rho is the dark matter mass density. This is the thing that we have some measurement of in the neighborhood of the Earth. That comes from astrophysical measurements of the distribution of stars. Here are the masses of the dark matter target and the nucleus. We've converted the number density of dark matter, which comes into the cross-section, to the dark matter mass density, since that's the thing we can actually measure. And our overall rate is also going to scale just with the number of target nuclei that we have available. So we'll call that capital N T. Okay, so this is our observable. The thing that we're actually trying to constrain is tucked into this part of the equation. So what is actually plotted on those y-axes? It's an effective cross-section for scattering on a single nucleon, where you essentially say, okay, the effective cross-section for scattering on a single nucleon is what you would get for scattering on a single nucleus, a momentum transfer 0, rescaled by the difference in reduced mass between the nucleus and just a single nucleon, and dividing out by this coherence factor 1/a². So that's the actual quantity that's bounded on those plots. So in terms of the FP and FN parameters that we wrote down before, when people talk about a single nucleon cross-section, this is what they mean. So if you have a particular model for how dark matter interacts with protons and neutrons, and you're trying to work out how that relates, like how LZ or how xenon or something has constrained your model, this is what the y-axis on this plot translates to. So in terms of that cross-section, we can write the observable spectrum that we see in this form. It depends on the form factor as a function of recoil energy. It depends on the density of the dark matter, the velocity of the dark matter. It depends on the mass of the nucleus that we're running into, so the mass of the target and the number of particles in the target. It goes inversely with the mass of the dark matter, just because as the dark matter mass dials up, you have fewer dark matter particles to interact with. And in this case, assuming spin-independent scattering, it scales coherently as a squared with the number of particles. So that's the set of standard assumptions that goes into the direct detection case. So there's one more thing that I've written. There's one more thing that we have to do. So here we have this 1/VREL factor. But you might very reasonably ask, all right, so this is meant to be the relative velocity between the dark matter and the target, but how do you know what the relative velocity is in any one interaction? And of course we don't. What you can do instead is say, okay, we're interested in understanding the spectrum of scatters. That spectrum of scatters will depend on will depend on the relative velocity in any given interaction. So we should integrate over the distribution function of possible velocities. So really, we should understand this expression that we wrote down out here. Rho is like the density of the particles with a given relative velocity. If there was just one relative velocity, this would be the correct expression, with rho being the full dark matter density. But more generally, we should understand it to describe the mass density of dark matter particles with a specific relative velocity, and then we should integrate over the relative velocity parameter. So that means, in this expression, we have a 1 over VRL dependence. That's going to turn into an integral over 1 over V times the phase-space distribution for the dark matter velocity, f of V, integrated with respect to V. And this distribution will be determined by the astrophysics. This is determined by how dark matter moves through our local halo. So the final result, which I think you saw in a previous introductory talk last week, looks like this. Our final rate of scattering in the target as a function of recoil energy, it depends on the target properties. It's advantageous for purposes of overall reach to have heavy targets, a large number of target nuclei, and a large coherence factor, a large A squared, so a large atomic number. It also depends on the form factor to some degree, although this form factor turns out to mostly only be important for pretty large recoil energies. It depends on the dark matter properties, so the scattering cross-section between the dark matter and nuclei combined with the reduced mass of the dark matter nucleon system and the dark matter mass, but the zeroth order scaling with dark matter mass here is just this 1 over m chi. And it depends on the astrophysics and on the velocity distribution, and this velocity distribution is where the dependence on the, is where some of this recoil energy dependence comes in. So let's have a look at the so this is how to calculate our spectrum of recoils as a function of energy. Let's take a closer look at what it should look like. So the shape spectrum of the spectrum is going to come from 2 places. So like, where is the actual ER dependence in this expression? So there's some ER dependence here in the form factor. That's going to matter particularly at high recoil energies. It tends to suppress the spectrum and add structure at high recoil energies. But the other place is that while I haven't written it explicitly here, this integral over the velocity depends on R, depends on the recoil energy, because we know that, well, let's just work it out. So that astrophysical piece, we want to do an integral over 1 over V times the distribution of velocities in the halo. That is an integral between some maximum velocity and some minimum velocity. The maximum velocity in this distribution is going to be determined by how fast the dark matter particles can go without escaping from our galaxy. Okay? But the minimum velocity, as we said before, so this is the minimum velocity that can contribute to recoils at a given energy. And that, we worked out earlier, it's related to the recoil energy by this factor. So this integral has a secret ER dependence hidden inside it. There's also a time dependence in this velocity integral, which is where annual modulation effects come from. So we're doing this integral here in the frame of the Earth. This is a measurement of the relative velocity, well, really in the frame of the lab. So this is the relative velocity between your dark matter particle and the nucleus that it is hitting. So since Vmax is the galactic escape velocity in the frame of the lab, that is slightly time dependent and slightly direction dependent as well. Okay, so let's just put in, as I told you, there's often a standard estimate that we just have a Maxwellian distribution for f of v in the galactic halo. So if we make that assumption, let's put this in and see what we get. Let's for the moment ignore the Vmax cutoff. We'll just take Vmax to infinity and so that we can do the integral analytically and see what happens. So in that case, we're going to take f of v to just follow a Maxwellian speed distribution. So this is this v squared e to the minus v squared over v naught squared. Then we can do the integral analytically and it just turns into an exponential with the recoil. So again we see we've got e to the minus er, and then the scale of er is set by the reduced mass squared times the velocity, the typical velocity dispersion squared divided by mn. So this is sort of minus ER over the sort of like typical ER. Okay, so what we expect to see, if we ignore the form factor effects, which is the other place where the ER dependence comes in, is a smooth exponentially falling spectrum, then multiplied by the form factor squared. So this is an example of the kind of behavior that we expect to see. So this is as you dial up the dark matter mass, this is the recoil energy, this is the spectrum of rate with differential with respect to recoil energy that you would expect. The curves down here correspond to light dark matter. So as we discussed before, for light dark matter, the characteristic scale of the recoil energy is really small. It's easy to hide this under the energy threshold of the experiment. For heavier dark matter, the spectrum eventually becomes independent of the dark matter mass because the reduced mass of the system only depends on what is lighter between the dark matter and the target nucleus. So for sufficiently heavy dark matter, all these curves are going to look more or less the same. This extra behavior at very high recoil energies is coming from the form factor. So again, just a couple of things to note from this. So even if you've got really heavy dark matter and the characteristic scale of the recoil energy is 10 to 100 keV, as we talked about before, it's still true that your spectrum is exponentially falling. So having sensitivity at low energies is really important. Your generic expectation, even for heavy dark matter, is that a lot of your signal is going to come in the lowest energy bins. For light dark matter, this is even more critical because the scale of this exponential fall off is very small. And so if you don't have low energy sensitivity, you just have no sensitivity at all. Okay, so if we want to, so that's the spectrum. This is what our signal will look like, looking for elastically scattering dark matter bouncing off nuclei. We can also just do a parametric estimate for what the total rate is. Let's just ignore the form factors for the moment. We've just said that the form factor only really affects what's happening out on this exponential tail of the spectrum. So let's throw away the form factor and just say, okay, if you integrate over this recoil energy, how many total events would you get? Within this approximation that we've made for the velocity distribution, we can do that analytically. We get a result that looks like this. Now, of course, in reality, you wouldn't do it this way. You would put in the full velocity distribution, including the cutoff, and potentially considering something more sophisticated than just a Maxwellian distribution. But if you do that, you consider if I do see a volume of, say, 100 kilos of xenon, then you can ask what kind of cross-section do you need to, you can ask what kind of cross-section would you need to see one event per year for a 100 GeV WIMP. Our target, our number of nuclei in the target is going to be just Avogadro's number. So a mole of xenon turns out to be about 100 grams. So with 100 kilos of xenon, we'll have 1,000 times Avogadro's number, atoms in the target, so that's about 6 times 10 to the 26. Our mass of our target is about 100 GeV. If the WIMP is also about 100 GeV, the reduced mass is just about 50 GeV. The local density of dark matter is usually estimated to be about 0.3 to 0.4 GeV per cubic centimeter. So again, that comes from like observations of stellar motions from our galaxy. The reduced mass, but with a single nucleon, is going to be about 1 GeV, because that's the mass of a proton or neutron, and that's much lighter than the dark matter in this picture. And we'll take V0, the velocity dispersion, to be about 200 kilometers per second. So if we put in all those numbers into this estimate for the overall rate and do a little bit of algebra, what we end up is a result that looks like 10 to the 46 times sigma chi n per square centimeter per year. So in this case, if we waited with 100 kilos of xenon, if we waited for a year and we had a cross-section between dark matter and nucleons, as defined previously, again, this is kind of this averaged result over protons and neutrons. It's, But if we had this kind of parametrization for the average scattering rate, if this sigma was 10 to the minus 46 square centimeters, you would expect to see about 1 event a year in 100 kilos of xenon. Have a larger volume of xenon, you can get to smaller cross-sections. So this is the basic idea between these big noble liquid experiments. Okay, now things that we left out. We threw out the Vmax in our integral. We also, I also sort of hand waved the difference between this velocity dispersion that I showed you. This is this is isotropic. This is an isotropic velocity dispersion, and that's relatively true in the galactic frame. It's probably not true in the lab frame. So to do this right, we should take into account that the lab frame and the galactic frame are not the same. We should take into account the motion of the lab through the galaxy. If you do this correctly, you need to include the time dependence and the asymmetry of the velocity distribution as seen from the Earth. Our galaxy has a finite escape velocity of about 500 to 600 kilometers per second. And the lab obviously is on the Earth, which is moving around the sun, and the sun is moving around the galaxy. So this famously leads to an annual modulation effect, where when the Earth is moving into the wind of WIMP, or when the Earth and the sun are sort of moving together through the galaxy, you get an enhanced signal. You get when they're moving opposite to each other, you get a reduced signal. So if we were to look at the log of the rate as a function of the recoil energy, then you expect the slope here to just tilt a little bit at different times of the year, and we can look for that as a modulation signal. So that would be a cross-check on a possible signal that we saw, or it could be treated just as an independent search. Okay, so that's the basics of how direct detection works. So we can use this to see, okay, what kind of strategies do you need? If you're looking for spin-independent scattering, you want large volumes and lots of A. However, having lots of A, large atomic numbers, it does make you worse at finding light dark matter. It gives you bigger boosts for overall coherent scattering, but if your target is heavy, then it's going to be harder to see light dark matter particles scattering off it, since there you care about the ratio between the mass of the dark matter and the mass of the target. You'd like to have low backgrounds. So the backgrounds here, neutrons scattering inside your detector mimic nuclear recoils but can be shielded. Photons and electrons scatter dominantly off electrons, so in these big experiments you need to distinguish between electron and nuclear recoils. And in the future, these experiments are going to get good enough that neutrinos are actually your background. And that's a more difficult background because we don't really have a good way to screen those out. The current flash experiments have done a really good job on reducing their backgrounds to basically zero or near zero, primarily by identifying and rejecting these electron scattering events. And the key strategy for that is usually to measure two observables where the behavior of electron and nuclear recoils differ. So for example, in liquid noble gas experiments, you can look at both ionization and scintillation light being caused when one of the nuclei within the medium recoils. Super CDMS uses silicon germanium semiconductors, and there you measure both ionization. I think that should be phonons. But it's also true. So this is a really good way to reduce background, to have sort of like two independent things that you can measure and use that to distinguish the nuclear from electron recoils. But if you want to go to really low energy scales, it may be, or really light dark matter masses, it may be advantageous to avoid some of those background rejection techniques, except that you will have a background, but have sensitivity to lighter dark matter. So there are studies that you can do where you essentially use just one of these measurements, and that allows you to get to a lower energy threshold. I think this was discussed a bit more in one of the previous talks, but at the moment, we don't have any convincing positive detections in direct detection. The Dama Libre experiment had a long-standing claim detection of annual modulation, but it wasn't background-free. It's difficult to reconcile the result with limits from other experiments, and there are currently some attempted direct replications. The one that's gotten furthest is NAS 1112, and they don't really see anything clear in it, and what they see seems to be in tension with the original Dama results. There's a nice Snowmass paper that talks about puzzling excesses generally that has a section on this. Okay, so that's the basic framework of how we do direct detection, of what matters, of what is meant on that y-axis plot. This is what our expected sensitivity looks like to the cross-section at 200 GeV over a time scale of the next 10 years. So, and you can't, okay, sorry, there is an important gray band on this which is visible on the screen but not visible on the projector. Okay, Okay, the grey band is basically just sort of mapping out where we're going. So solid circles on this are showing current sensitivities of a bunch of experiments. The blue regions here are showing xenon-based liquid noble experiments. So they use xenon, which is a high mass target. They use large volumes of highly purified liquid xenon. The LZ experiment is this little point here, and then the squares are where the current experiments will get to if they run for their full if they run for as long as they are expected to run for. So that's their eventual sensitivity goal. The red points here are using a different liquid noble gas, so using argon. So as you can see at the moment, the xenon experiments kind of have an advantage, but argon's a good competitor, and in the future, if we do see a signal, it would be really helpful to be able to see a signal in more than one target material. That would allow you, for example, to try to disentangle the scattering on protons versus the scattering on neutrons. These lines down here are where the neutrino fog or the neutrino background lies for argon and for xenon. This is where you would expect to start detecting the neutrino background. So the current generation of experiments are actually going to get pretty close to this point. These future planned experiments like Argo and XLZD would be the neutrino fog explorers for xenon and argon respectively. And so here we are in 2022. The current generation of experiments, LZ and xenon n-ton, should finish their runs in a few years. And then XLZD and Argo are the targets for about 10 years from now. So this neutrino fog sensitivity corresponds to cross sections around 10 to the minus 48 square centimeters at this particular mass at 200 GeV. So this is a place where over the years there has been enormous improvement in these cross-section bounds. And we've still got a little way to go before we hit the neutrino floor, but probably on a 10-year timescale, we should be getting to the point where we start running into irreducible backgrounds for these searches. So what can you do with that? Well, I talked about benchmarks for this classic WIMP region last time. So this is an analysis of some models within the phenomenological minimal supersymmetric standard model back in 2013. Each of these points represents a point in parameter space. And again, this is a specific restriction of the minimal supersymmetric standard model. This doesn't capture all possible SUSY models. This captures just a subset. And I think in this case, they were also not excluding models where the neutralino was not 100% of the dark matter. So this includes cases also where the lightest neutralino is some subfraction of the dark matter. So what they're plotting here is the cross-section in direct detection multiplied by the fraction of the dark matter that is made up of the lightest neutralino. So that populates this ensemble of cross-sections. This blue, so just for calibration here, this is expressed in picobarn. 1 picobarn is 10 to the minus 36 square centimeters. So the neutrino floor is about at this 10 to the minus 12 level, at least at a couple of hundred GeV. So you see that in this case, the existing experiments, which are, the blue line is where LZ should get to, they can rule out a significant amount, but not all, of the SUSY parameter space. If we get down to the neutrino floor, we'll be doing better. But there will still be models within these benchmarks whose direct detection cross-sections lie below the neutrino floor. This isn't a panacea, it doesn't capture absolutely everything. The good news is that a lot of those models are testable through other strategies, that accelerators are in indirect detection. So this is not the only tool that we have, but this is one very powerful tool that we have. This is another example using those minimal dark matter benchmarks that we looked at earlier, where you just add additional SU2 multiplets to the standard model. So the current constraints are about up here. This is now a mass scale from 2 TeV up to hundreds of TeV, so this is on the heavy side of the classic WIMP region. This green dashed line is where LZ is going to get to. The neutrino floor is down here, about an order of magnitude lower than the reach of LZ. This line here is the Darwin, so XLZD. This is the big flagship next generation xenon experiment. This is their expected sensitivity reach. And so you can see that in this case, if we could get down to the neutrino floor, you actually would be able to pretty comprehensively test all of these minimal dark matter scenarios. So all these cases where you just add extra SU2 multiplets to the standard model, we wouldn't have found them yet. There's no reason to think that any of these should already have showed up in direct detection experiments. But if we can get to the neutrino floor, we should be able to get them. Okay, so I am coming to the end of my time, so I think I'm going to just say a little bit about this, and then I'll continue with the discussion this discussion after the break. So everything that I've told you so far is like the standard wisdom. It's a talk that could have been given, that mostly, except these last couple of slides, could have been given 10 years ago or 20 years ago on how we look for nuclear equals. But as we've discussed, we haven't found WIMPs. We haven't found classic WIMPs yet. We haven't found them at the LHC. We haven't found them in those direct detection experiments. Although, as these plots show, there is still a fair way to go. There are some pretty simple benchmarks that we wouldn't necessarily expect to have seen yet. But nonetheless, there's been a great deal of interest in recent years in saying, all right, so what if the signal that we want to look for is not scattering of dark matter off nuclei? What if dark matter is substantially lighter than 10 GeV? So we've said that searches for elastic nucleus dark matter scattering are pretty inefficient for light dark matter due to this kinematic mismatch, due to this suppression by the recoil energy by the dark matter mass squared divided by the target mass. So what can you do to deal with that? Well, first, you can note that when these nuclear recoils happen, they're not always fully elastic on the nuclear side. You can have photons get produced by bremsstrahlung. You can get extra electrons produced by what's called the Migdal effect. So that can give you an extra set of signatures to look for just for nuclear scattering, which can sometimes provide some sensitivity to lower mass dark matter. But another pretty obvious thing you can do is say, okay, what if we use electrons as the target instead of nuclei? What if we look for the signals of dark matter particles bouncing off electrons and causing them to recoil? Electrons are 500 keV, so they're a factor of 2,000 lighter than nuclei. So that can potentially get you down to sort of MeV scale dark matter instead of 10 GeV and heavier dark matter. Again, the lesson here is just it's good to look at recoiling. If you're looking for elastic scattering, it's good to look for recoiling targets that have a mass similar to the thing that you're trying to bounce off them. So the danger there is we don't have all the tools for electron recoils that allow us to reduce the background for nuclear recoils. So there are going to be backgrounds. Experiments searching for nuclear recoils have, seen in some cases some unexplained backgrounds. But that's something we need to understand. Another possibility is maybe the way that the dark matter primarily interacts with these targets is not by scattering. Especially if dark matter is very light, you can have models where the dark matter just gets absorbed onto standard model particles. So in that case, the energy transfer would be order of the whole dark matter mass, not just the dark matter kinetic energy. So absorption searches can allow sensitivity to much lighter dark matter. More generally, what you need to do to look for light dark matter is to be able to see really tiny energy depositions. So there's a really active research program underway in how to find possibly observable signatures of arbitrarily tiny energy depositions. And often that means using a special target material, something that has, for example, a very, very tiny band gap across which electrons can be excited. This is so there is a nice review of this by Essig et al. From the SNOMAS process. This is sort of showing the recoil energy in electron volts that you expect to be able to probe at liquid noble bubble chambers. So this is sort of a keV at the top of the plot. This is the classic WIMP scale recoil. You can look for, at lower recoil energies, you can look for ionization in semiconductors and insulators. At even lower energies, materials with very tiny gaps, searches for optical phonons. And if you can, with superconducting nanowires and with superfluids and with single phonon detectors, you can hope to get all the way down to sort of milli-eV recoils. So this is just one. So this is one example of an experiment that's actually running that's come out of that program, which is called SENSEI. So SENSEI takes advantage of recent advances in the development of really sensitive ultra-low noise devices called skipper CCDs, so skipper charge coupled devices. So these are based on silicon. Silicon has a band gap of about 1.2 eV. Recent advances in detection technology basically allow you to have these CCDs with millions of pixels, which are sensitive enough that you can detect single electron excitations in any one of those pixels. So you can measure the charge in each pixel with sub-electron noise. I don't know the details of how they do this, just apparently you have these magic devices that can measure that can measure excitations across the band gap in individual pixels over a 1 million pixel system with sub-electron noise in each pixel. So then the search that you can do is say, okay, let's look for single electron excitations across the band gap. So here, the idea is a dark matter particle comes in, it hits an electron, it scatters it up across the band gap, you measure the charge in that pixel, you measure the charge in every pixel, and then you look for the same kind of characteristic signal that we've been talking about in the context of nucleus dark matter scattering. So this lets you test dark matter electron scattering down to masses of about 500 keV, so similar to the electron mass. It lets you dark matter nucleus scattering, which can, when the nucleus recoils, it can produce a bunch of electrons associated with it. You can look for those as well. So that actually allows you to get some sensitivity to DM nucleus scattering down to relatively low masses too. And you can also look for dark matter absorption electrons down for mass scales of about 1 MeV. So this upper plot is showing the like the distribution of excitations across pixels. So this charge V minus corresponds to a single electron excitation. These higher ones correspond to multi-electron excitations. By setting an upper limit on the number of single electron excitations that have, Sensei set this bound. So this is the cross-section for dark matter electron scattering as a function of mass. And you can see that their bounds, they die off around 1 MeV, as you might expect. But the top of this axis is the GeV scale. And this solid line here is the freeze-in benchmark that we were talking about at the beginning. So this is freeze-in through an ultralight mediator. So we're not quite there yet, but pretty close. Okay. And so over the next 10 years, as I said, there's a huge research program looking into this. These plots are just showing the sensitivity that we currently have with existing bounds. That's the pink regions. This is through a combination of cosmic and astrophysical bounds and existing direct detection searches for relatively light dark matter. So on these 3 panels, this is dark matter electron elastic scattering. These 2 are both dark matter electron scattering. The top panels where you've got a heavy mediator, the bottom panels where you have a light mediator. The right-hand side is dark matter nucleon scattering through a heavy mediator. So these are the constraints from the classic WIMP searches that we talked about before. And these bottom panel is for dark matter absorption onto the target. So I think this is specifically for dark photon dark matter. This is the freeze-in benchmark that we talked about before. These are, I think, freeze-out based benchmarks. So thermorelic benchmarks. So this green region is basically what experiments using existing technology like Sensei and scaled up versions of Sensei can do in the near future. The blue region is what we can do if we can actually get these sort of superconducting nanowire experiments to work with sensitivity down to milli-eV depositions. Okay, so let's stop there for the moment. I'll take any questions, and when we come back, I'll talk about accelerators and then about axions.
Okay, so we ran a little bit over time.
Yeah, no, sorry, I wanted to get to this part.
Yeah, but we can postpone coming back from the coffee break for 5 minutes, so we can have at least 5 minutes of discussion. Okay.
Thanks for the lecture. Just to clarify, if the coupling of the dark matter with the nucleon or the quarks does not happen at 3 level, that allows you to have bigger masses and still do not, let's say, avoid this constraint?
I mean, so these are just constraining the cross-section. So, and that cross-section could be obtained through a tree-level process, it could be obtained through a loop-level process. But so just as an example, these minimal dark matter benchmarks, all of these, the dominant scattering is through a loop of W bosons. That's why the cross sections are as small as they are. I think if you look at these like SUSY models, a lot of these points that are ruled out, the scattering will be tree level through the Z or the Higgs, and a lot of these points that are not yet ruled out, the scattering will be going through a loop. So the idea here is that what you care about is just what the scattering cross section is. Within your model, you know, within your particle physics model, you'll get predictions for what like FP and FN should be. Those could arise at tree level, those could arise at loop level. They could have some dependence on momentum, which we haven't factored in here. If you put that in, you know, that would give you some additional dependence on the momentum transfer. The statement that we have is that we can exclude this quantity being higher than about 10 to the minus 47 square centimeters.
I have actually a question where I go with this FP and FN. So besides particle physics information about the couplings and so on,
Yeah.
I guess there is also some kind of non-perturbative QCD stuff. No, that if it's 0, for example, we could be swimming in dark matter and we will never see it, right? I mean.
Yeah. So right. So what goes into this FP and FN is you need to know how your dark. Yeah. So if you have a way to just say, here's how my dark matter couples to protons and neutrons, then you're done. Great. But the way that you typically need to compute this is you figure out how your dark matter scatters off the various quarks in the nucleus, and then you need to know what the quark content of the nucleus is, which you get from lattice calculations and from various nuclear physics estimates of what their content is. And there can be significant uncertainties on that, actually. And things like, I remember if you're going through like Higgs portal dark matter, for example, you care what the strange quark content of your nucleus is because the Higgs couples to strange quarks better than it does to up and down quarks. So you could have a situation where the dark matter hates to couple to hadrons and likes to couple to electrons, for example. In that case, you'll get very small cross sections in these nuclear scattering results. But although maybe you'll get some, maybe you'll get something non-negligible through the Migdal effect, or the electron scattering experiments could go after them. You can have scenarios where the dark matter scattering cross section is just super tiny to all the particles that you might think about in the standard model. The example of that I'm aware of is the Higgsino, which is actually not shown on my plot of benchmark models, but a near pure Higgsino has a direct detection scattering cross section that is just below the neutrino floor, actually. So it's the one that is going to be somewhat hard to get to with direct detection. Although if it's not quite a perfectly pure Higgsino, it can be a lot easier to see. But there, what's going on is just that there happens to be a cancellation between two diagrams. Diagram 1 is like a single loop of W bosons. Diagram 2 is a two-loop diagram involving the gluons in the nucleus. And with our best current estimates, those two happen to cancel each other out to good enough precision that the cross-section is below the neutrino floor. And that's just a coincidence. There's this really... it's a good paper, but it's kind of depressing from 2011, which is, before we were really sure of exactly what the Higgs mass was, that shows the Higgsino scattering cross-section as a function of the Higgs mass. And it looks like, there's this big dramatic dip in the cross-section. The sort of theory prediction for the cross-section looks like this, where here's the neutrino floor, here's the cross-section, and this is as a function of the Higgs mass, and this is 125 GeV. So it's just a coincidence. It just happens that in our universe, 125 GeV Higgs leads to a really tiny scattering cross-section for the Higgsino. So again, this is one of the reasons why we do multiple types of searches. It is true that you can have particle physics models where these numbers are just very tiny and you wouldn't have seen them yet.
So maybe you said it at the beginning and I missed it, but can't the dark matter particles be produced via freezing from annihilation from the standard model particles, or is there something that forbids it to produce them directly?
So you can have I think effectively yes. So the thing that you want to avoid with at least like infrared dominated freeze-in is a situation where the where all the production happens at really early times, right? Like where you know where the rate of production is much higher early in the universe, because then when you extrapolate back to earlier times, you tend to get into a situation where you would have been in thermal equilibrium at earlier times. So you never want to get to thermal equilibrium. So you don't want something that for which the rate scales up quickly as you go to higher temperatures. That said, so and that eliminates some possibilities for annihilation, because if there's no temperature scaling in the annihilation rate itself, the generic annihilation goes like n squared. It gets more effective at higher temperatures. But I think that so if you the sort of classic benchmark for freezing that looks at in this Dworkin et al. Paper is either the dark matter has some tiny millicharge, or it couples through an ultralight vector boson, whose couplings are suppressed in the early universe. And yeah, so in that case, the production mechanism is basically standard, for the millicharge case, for example, is basically standard model photons annihilate into millicharged particles. Or you can get these effects where basically standard model photons have some plasma mass in the early universe, and the plasmons actually decay into dark matter particles, and that's also a production mechanism. So, yeah.
Okay, thanks.
Okay, I think let's move on to the coffee break, otherwise it's gonna be too late. So thank you, Tracy, again for the next lecture. So should we come back at 35? Okay, so we have 5 more minutes, but